Hello and welcome to our lesson on sketching the graphs of reciprocal trigonometric functions. By the end of this lesson, you will be confident in sketching the graphs of cosecant, secant, and cotangent. Before we go forward with the trig graphs, though, I want to dive back into some of the knowledge that we gained in our rational function unit. When you were asked to sketch a reciprocal function from the graph of a polynomial, you did not need an equation because all of the output values, all of the y values are visible there. And so we learned a set of steps that allowed us to accurately sketch a reciprocal function. The very first feature we would put on our graph of our reciprocal function, if this is my graph of f at x, then in order to graph 1 over f at x, which is a reciprocal of f at x, we knew that wherever my f at x is calculating out a 0, if I put that 0 output into my denominator, then I would have a 1 over 0, which is going to be undefined. And so where my original function has zeros, I would put my asymptotes, noting the areas where I will not have an output value for my reciprocal graph, there and there. And once we had our asymptotes on here, we also had looked at horizontal asymptotes of this class of graphs. Whenever I have a 1 on top, then I'm putting my inputs down here into f and x, and I will always have 1 out of a number, which means that y will never calculate out to 0. If I always have 1 out of some number, then I can't calculate out a 0, and so we put our horizontal asymptote at 0. Now remember that horizontal asymptote effect, where my dots approach it but never meet it for the values of my function, only happened for the end behavior of my curve. It didn't happen in this central section. And then I was looking for test points. The easiest test point, the easiest value that I would put in the denominator would be a 1, because if I could find where my function is a value of 1, 1 over 1 is still 1. And so my reciprocal function shared the 1's, so there is a value of 1, and 1 over 1 will be 1. And I don't have any more positive ones, but certainly if I put a negative 1 in that denominator, I would share that value. 1 over negative 1 is still a negative 1, and about there my function is a negative 1 as well. So I've got a couple test points in each of the regions of my graph. But then to find the rest of my function, I had to remember some rules about rational functions. Wherever my original function will be increasing, my reciprocal function will be decreasing. And so I know that the values of in this section will constantly be decreasing. If I wanted to have something that was relatively accurate, I might say, okay, well, what is a base graph dot or a parent function dot here? This looks like almost 5. About here, it's a negative 5. 1 over negative 5 would mean my rational function would be up at a negative 5th. Again, if I wanted a relatively accurate test point in this region, I might find, oh, about there it looks like it is that input created a negative half. 1 over negative half would result in a negative 2. And so my reciprocal graph would be about there. And I know that I would approach but not meet the values of my asymptotes. And so the behavior in this section is generally decreasing when my parent function was increasing. Here I am decreasing, so my parent function is going to increase. I have a very tiny number close to this asymptote, as I did on this side. And 1 divided by a very tiny number, how many tiny numbers are in a 1? Well, that's a relatively large number. If I have 1/1,000,000th, how many 1/1,000,000ths are in a 1? Well, that would be a million. And in this section, we are a negative value. Wherever my parent function is negative, my rational function will also be negative. And so if I wanted to look at a very tiny amount here, it means that 1 over a very tiny amount is going to be, decreasing from my 1 here. This value is a negative half, and so a negative half in the denominator will result in a negative 2, and I know that I will be approaching but not meeting the value of that asymptote. As my parent values are very tiny negatively, they will be very large negatively in a reciprocal function. Similarly here, my parent function is increasing, so my reciprocal function will be decreasing. I'm at about a negative half here, which means my negative 2 for my reciprocal function will be very close to my asymptote, and I will approach it but never meet it there. On this side of my vertical asymptote, my parent function is positive, and so 1 over positive numbers will remain positive. My parent function is increasing, so I know my reciprocal function will be constantly decreasing, approaching but not meeting the values of its graph. If I wanted something that was relatively accurate, this looks like a positive 4, which means my reciprocal function will be down at a positive 1/4. Those are a reminder of all of the rules that we employed in order to write to draw the reciprocal function of 1 over a polynomial. We are now going to be graphing reciprocal functions of trig functions. And so we're not going to have a polynomial in our denominator. If we want to graph the graph of cosecant, it is simply the reciprocal 1 over our sine function. Secant is a reciprocal of cosine, and cotangent is the reciprocal of tangent. All of the rules that we employed in finding the reciprocal of a polynomial are going to come into play for finding the reciprocal of a primary trig function. Finding the cosecant, secant, and cotangent are just reciprocals of sine, cosine, and tangent. So let's do this graph together, and then we will, I'll set you loose to do secant and cotangent on your own. But if we're going to graph cosecant here, first let's sketch very lightly the graph of sine. And I say very lightly because the graph of sine is not part of the graph of cosecant. And so I'll do sine lightly just to remind me of the output values of my original parent function. My original parent function will be sine. So sine starts at its 0, ends at its 0 at 2 pi radians, with a 0 in between. Halfway in between its first two zeros, it hits its maximum of 1. Halfway in between its last two zeros, hits its maximum of, that's halfway, maximum of -1. Sketch it lightly. It's not part of cosecant, but it will help me to figure out cosecant. Now, nice light sketch here. We might even want to erase it afterwards, but there is my graph of sine. If I want to remind myself of the major values for sine, sine starts out at a 0, ends at a 0, 0 in between. The sine of pi over 2 is a 1. The sine of 3 pi over 2 is a -1. The sine of pi over 6, if we remember our special triangles, pi by 6 and pi by 3 are 30 and 60 degree angles in our old language, has our 1, 2, √3 triangle. And so the sine of pi by 6 is 1 over 2, which is why we're up at about a half there. Exactly a half. 5 pi by 6, again, will be a positive half because it is a 5 pi by 6 angle in my second quadrant. There's 5 pi by 6. It uses a pi by 6 reference angle, so it will have the same numbers as my pi by 6 reference angle, and of course in those first two quadrants sine is positive, so sine values are positive. Our unit circle connects with the graph of sine, and so that will also be a half. And then 7 pi by 6 will also be using our pi by 6 reference angle, but it's in a quadrant for which sine is negative, and so down here it will be a negative value, -1/2. And again, 11 pi by 6 will be a -1/2. I put those on as key values because those will be useful in graphing cosecant. So there is our parent function. We are going to use the very same logic as our polynomial reciprocals as using a sine reciprocal. The reciprocal of sine, 1 over sine, is cosecant. And so if I have an input of 0 and I'm wondering what's my cosecant value, well, that is a value of 0. And so 1 over a value of 0 is going to be an undefined value. That is going to happen at 1 over 0 is going to happen at 0, at pi, and at 2 pi. visually, we know, looking at our graph, wherever our parent function has that 0, I will have an undefined value. So we'll put our asymptote there for all of our zeros. So the first 2 pi radians of cosecant has 3 asymptotes. Next, we want to find some test points in those regions. Our test points in those regions, we will look to the easy ones. Well, there's a 1. So 1 over 1 is also going to be 1. And here I had a negative 1. 1 over negative 1 is going to be a negative 1. So we'll again share the 1s and negative 1s. Then if I want some more accurate test points, let's look to my half values. If I have 1 over a half, I'll invert and multiply that. Or if I think that sine is opposite over hypotenuse, then cosecant is hypotenuse over opposite, and that is a 2. So at the pi by 6 reference angles, we will head up to values of 2 because my original parent function was up a half, or down a half will go to negative 2. Down a half goes to negative 2. And so then, in order to approximate where are all of my other million billion dots in between, then I need to just approach my asymptotes. Nice smooth curve through there. And there is the graph of cosecant in the first 2 pi radians. Now, to truly show the graph of cosecant, I would get rid of this graph of sine because it has no place in the graph of cosecant. Key features for cosecant? Well, for key features, we always need to talk about asymptotes and intercepts and any kind of domain and range, those kinds of things. And so if I talk about the domain, first of all, the domain of cosecant is not all real numbers like sine. The domain of cosecant is interrupted by its undefined values. The undefined values, this is one full cycle of cosecant. That happens again over here and again over here. I'll show you that on Desmos in a second. But the domain of cosecant repetitively has these values that are undefined. And that happens in a half cycle. And so we would say, we're using x or theta. Well, I've kind of got a mix of both. Why don't we use theta consistently? So theta comes from the set of real numbers, but theta is not going to be allowed to be 0 and pi and 2 pi. It's every n values of pi, as long as n is an integer. Because I can't expect to have a 3/4 set of pi's and find an asymptote. That doesn't happen. And then my range is a little bit complicated here as well. The range of cosecant, sine was below or above my 1s and negative 1s. It was everything between those values. Cosecant is not that way. It is everything above a 1 or everything below a negative 1, so off to positive and negative infinity. Now you can write that in 2 separate associations, not theta, we want y. Our output values, our y values, come from the set of real numbers, so negatives, positives, decimals, fractions. But my y value has to be greater than or equal to a 1, and my y value has to be less than or equal to a negative 1. If you wanted to put that in one statement, you could say that the negative 1, my y value has to be less than a negative 1, but it has to be greater than a 1. You could put that in a single statement. If I want to talk about intercepts, for cosecant we have no y-intercepts and no x-intercepts. So no intercepts at all. Intercepts. At all. Vertical asymptotes at theta values where they are equal to my exclusions here. So it's at every set of pi's before and after 0. So my theta value would be equal to n values of pi as long as n is an integer. We could write it that way. It's the same as the exclusion in your domain. So in summary, and you are going to be, I guess I should fill these in. This would be 2 and 2 negatively. You're going to be doing the graphs of secant as well as cotangent, taking into consideration the rules of drawing a reciprocal function. Where the parent graph had zeros, 0 over 1, the reciprocal graph will have vertical asymptotes. The values of +1 and -1 will be shared by both parent function and the reciprocal function. So find those as your first test points. And where the parent graph is positive, here sine was positive, so cosecant is also positive. So where the parent graph is positive, the reciprocal graph is also positive. And where the parent graph is negative, the reciprocal graph is also negative. Sine was negative here, so cosecant is also negative. The sections where the parent graph increases, so the parent graph increases, are sections where my reciprocal graph decreases, and vice versa. So you are now going to be spending some time drawing the graph of secant. So I would suggest sketching cosine very quickly, very lightly, and using it as a guide to draw secant, and then find the key features of secant. And finally, cotangent is a little bit crazy, especially when you combine it with the graph of tangent. But very lightly, draw the graph of tangent from 0 to 2 pi. Now that is more than one cycle of tangent, but draw it from 0 to 2 pi, and we'll see what results from cotangent. Draw it very lightly, and then cotangent will be on top of it. Find me the key features for cotangent. And then I've provided another sheet just to reinforce the rules of reciprocal functions, but this time when you draw cosecant, secant, and cotangent, I would like you to draw just the reciprocal functions and not draw the primary sine, cos, and tangent first. So see if you can draw just cosecant, secant, and cotangent. Now I had promised to show you on Desmos, but I don't have my tablet here with me, so I apologize. But what I would ask you to do is to look on Desmos to see the graph of all of these functions, put them in there so that you can absolutely see that this is not just cosecant, that it continues on over and over and over again. Also, on our classroom website, I have included a video of another professor who does a good job of explaining graphs of cosecant, secant, and cotangent. And actually, at the very end of it, he has a very common an explanation of a common misconception in terms of how is this different than this in terms of what it's asking for. And so at the very end of that graph or that video on our website, you'll have an explanation of the difference between that type of notation. Enjoy making the graphs of secant, cotangent, and then graphing all of them alone.